Our guest speaker tonight is Dr. Daniel Brown. Dan is an associate professor at Nottingham, Trent University, teaching astronomy to undergraduates and postgraduate students. He also runs the NTU Observatory on their Clifton site, their portable digital planetarium, and numerous other outreach courses. His areas of research include controlling light pollution and heritage of the night sky. And he works closely with local, national and international press regarding astronomy, including a monthly slot, as has been mentioned, on Notts TV every last Tuesday of the month. And for those that didn't realise it, that's today. And Dan did this this evening's talk from right here in our society before the event. His talk this evening is entitled The Bromley Meridian. So please give a warm MSAS welcome to Dr. Dan Brown.
Thank you very much. I'll just pause my little intermezzo that was going on in the background and bring up the slide. So thanks for introducing me. Yeah, I'm Dan Brown. I look after our on-site observatory in Nottingham Trent University. Some of you might have seen it as well, but part of my work is also doing a lot of public engagement, outreach, and, for example, looking into the history of astronomy into the very prehistoric times, but also in more modern times, and one of which is about only looking at a few hundred years back, where we are covering some of the fascinating installations that we've come across, also in not only in the UK in general, but also specifically at a site in the city centre. So this is Bromley House Library, and in there's a meridian. I'll kill the lights so we can now start to see this a little bit more in detail. So today's talk will be all about the Bromley House Library Meridian Sundial that's in there, and telling you a little bit more about what these Meridian Sundials are, where they are, what they're used for, and possibly giving you an idea of what the background is behind the construction of that and how that might have happened. So overall, a bit of, as I said, a lowdown on what these specific sundials are, because they're definitely not your usual sundials you've come across. Then there are 4/3 of these only surviving in the entirety of the UK. So we're quite lucky that we've got one just around the corner. We visited, or I have visited them all, captured a bit of survey work, and can talk a little bit about the quality, how they're set up, and in what state they are currently. When I say currently, that means that's probably a year to 2 years pre-pandemic where they are. One of them is then specifically our local one, which is housed in the Bromley House Library itself. I'll then elaborate a little bit on the work that one of my past students has done on the construction methods. So how would we try to construct something like that? There are some proposals that then are looked into how well they work, and I'll indicate that some of these construction methods leave behind possible indications of misalignments that are not intentionally misaligned. They're just an effect of how you might propose they were set up. And there's a hint that we might have spotted something like that in the Bromley House Meridian case. And I'll try to draw on some conclusions as well. I'll see how it goes. Maybe towards the end, I'll give you a little beautiful intermezzo, because we worked with the Institute of Physics and Bromley House Library together to create a little short video when the Institute of Physics created their new headquarters that was featured in their line of the sun and the history of time as well, where we can see a few more views of these different meridian lines throughout, and including a little bit of history and how that works. So I'll keep that little nugget for right at the end. So meridian sundials. So what's this all about? So for one, if we're talking about sundials overall, they are really useful because they are a way to give you time. The only problem, if you say problem, they'll give you what's called a local time. Because you set up the sundial in your back garden and you read off how late it is and you check, and it's good. It tells you exactly the time as you want to for your garden. Therein lies the problem, because the UK consists not out of a single dot, but actually is quite widely spread. And if you look at the extent of the east-west, it's quite substantial. That's roughly 10 degrees in latitude that it extends from the furthest part in Northern Ireland over to the furthest part over here, Norfolk, Suffolk, in that side. So if you go in that one, even already when you're just noting little differences between Portsmouth and London, you've got essentially 16-minute time difference between a local time measured in Portsmouth with your sundial with in London, which you can see is a slight little problem, because if you're then thinking about expanding connection networks and introducing railway networks, you want to ensure that you have a meaningful communication when trains come in and timetables overall. And if you're thinking about the entirety of the UK, where if you're defining a time in the most western part of Northern Ireland and compare it to the most eastern part of England, you can have up to 40 minutes difference. So that's really not ideal. So we want to come away from that kind of local time. And that's where around about 1880s is where the act to make GMT, Greenwich Mean Time, the actual standard time, to be used throughout the entirety of the UK. There's more you can look into when you go into railway time and all of that, which were the first movements of trying to remove the local times into a joint overall time. And as we know, we're proud of our history and our localness. So there were always the little villages here or there, or towns that kept hold of their own time. So it took a while, but that gives you an idea that there was a move towards an overall fixed framework of time, as we have now as well throughout the UK and wider. But now comes the next problem. How do you set your clocks? Because if you set clocks, you would want to use your sundial to read off, but we know that's not right. So somehow we need to start setting them appropriately and having a sort of, as you would say, a time signal. Now, some of you will remember the good old times. You switch on the BBC and you get your time signal, the blips as they come, and then at that point you know that's the time. Then you have your clocks properly set. Nowadays you'll get time signals through the internet, or you get atomic clocks picking up radio signals and so on. So there's a certain way in which we pick up and synchronize clocks as well. But there's a need to set this, and especially if you're thinking about the times where we're just looking at the railway network joining up appropriately, there's a challenge how you would do this. So it's definitely looking into the motion of the sun and using these sundials to have a starting point to set your clocks. So for one is then realizing, well, okay, we can use the sun. The sun moves seemingly through the sky, which is a result of the Earth's rotation, seemingly moving the position of the sun around. So yeah, we can use the sun as it rises somewhere, I don't say east, somewhere in the east, over south to set somewhere in the west. So that's good. And ish, that's 360 degrees and 24 hours as it moves around. So if we're thinking about our usual coordinate systems on a sphere, that's brilliant. We're in here. There's our tilted axis of the Earth. So as things rise, they don't just go left, right. They go on a nice circular arc on that sphere as they move around. So plonk that little diagram on top of your little sundial pin that you might set up, and you can imagine that your cast of the shadow being cast is not a trivial straight line as it goes from left to right, but actually, there we are, if the sun moves on this arc around, you can see the appropriate shadow being cast follows this cone at the bottom. And as that cone of the shadow where it falls hits the ground, we now have the path of the shadow being a cross-section of a plane cutting through a cone. Hopefully that brings back avid and happy memories of school times, of doing geometry of that. And if you're thinking about that, that is not a trivial shape. So what you'll get there is a quite complex shape, and this is just one example of a sundial. There's the pinnacle, roughly 9 meters, 8 meters tall on a big flat surface, and these are the lines that the shadow will cast over a day. And you can see one example here. That's when Google Earth shot that picture. So there's a tip of it. And as it will move that shadow
will now follow that line as it goes around. The ones in the know will know this has been shot in the summer half of the year, as it will move across. You can see at different times of the year, you'll be at different points of that cone, and your cross sections will look different. Therefore, the path will not be simple and straight over a day as it moves across. So these are actually shapes that are related to hyperbolas, if you're familiar with them. Ever seen them, maybe? Possibly, who's seen a hyperbola shape? Depending, next time you, well, tonight when you're switching on your bedside lamp, have a look. You all have it. Because what I forgot to bring my little example of a little a torch just with a shield on the top. If you have a light source that sends a cone of light out that shines against your wall, you'll get automatically a beautiful hyperbola. So these are the shapes, and all I've done with my little model is, if that's my light source, I've put the neck of that paper cylinder further down, so it just sits level. You can see just with the light bulb, and you get a nice straight line because it's a nice hemisphere. Or I reveal it even more, and the lamp pokes out of your fitting, and there you get this. So what you're creating here beautifully is your hyperbolas, or your different shapes of the shadow as they pass through here. You can see as that happens. And these are all going to be just related to where the sun is in the sky. So if the sun is over here, i.e. in the winter half of the sky, there we are. At that point, your shadow will travel this cone. So we'll get our shadow path looking more, moving away from the cone, so open that way. In the summer, they're curved more towards us as the sun is higher up here and the cone is orientated down here rather than up here for the shadow. And we're getting these cross sections. You can see as they arc around your pin. And the beautiful in-between one is the equinoxes, where the sun moves nicely exactly around the equator. And at that point, if it moves exactly around the equator, it's on a nice plane, not a cone. And that means you've got one plane cutting through another, and you've got a beautiful straight line. And then all you have to do is have your appropriate lines going across here. That gives you an idea of times. And therefore, you've got a beautiful clock now set out. You can read off the time of year, seasons, months, and you can read off the time of day as well. But what it definitely isn't is a very simple draw a straight line, halve it in 12s, and out comes the time. So it's not a simple triviality. Okay, so far so good. If we can get a handle on that, let's move on maybe. Any flat earthers on here, you'll be horrified to hear what I'm talking about now. So solar time very much depends on your location. I mentioned it already, 10 degrees from east to west in the UK means 40 minutes time difference. Why is that? Let's have a look here. This is not to scale, neither in size nor distance. There's the sun, there's the earth. We're viewing the earth here from the North Pole onwards. So if Nottingham might be exactly here and the sun is high up in the sky midday, if we're looking at New York, that's offset. So at that point, New York just experiences the sunrise, where for us, it's above our head. So there you can see the nice justification why longitude has anything to do with the time in there as well. Only if you buy into a spherical Earth. If you're happy with that, it all works out okay. So that means at that point, we can really nicely define a local solar time. And that's why I said here, if you do the calculations, 1 degree is 4 minutes. So that's why 10 degrees over the entire UK gives you 40 minutes. So good. So far, so good. Yeah, nearly. So it becomes yet more fun. So who's ever seen these beautiful diagrams of the pictures of this kind of fig of 8 carved or drawn on sundials, an analemma? For those in the know, this gives you an idea of the slight complexity of how the sun moves. These pictures are captured beautifully by taking an image of the sun every time, every fixed instance in a day. So for example, at 12 p.m. At midday exactly on your normal clock, you will take a picture, and then the next month you'll take another one, and so on. And as that happens, you'll see clearly summer, sun is higher, Winter, the sun is low. That's fine. From our normal understanding, we would understand this. What we don't get is why that should be left or right. Bear with. So at this point, I'm going through that we're at 12 o'clock, taking a picture again and again and again. Now, if the sun seemingly moves around us at the same speed, that's fine. At that point, the sun should be exactly back at square one. There's a slight difference. Now, this is, if you're a fan of QI, you'll love this, and it's a good one for public quizzes as well. How long does it take for the Earth to rotate once around its axis? Let's see. Question. Have a quick think. I don't have a klaxon here that I can set up, but let's see. Good. Anyone tempted to say 24 hours? Yeah. It's not 24 hours. It's exactly this kind of what we would call a sidereal day, 23 hours, 57-ish minutes. And that's because the Earth takes that long to go once around. There's just one extra bit that we haven't taken into account. As the Earth goes once around, the Earth is now not in the same position with respect to the sun. It's moved one day on its path around the sun. That means what was up, let's say, in my very crude diagram, the sun is in that direction. So that's where I started my clock. I've gone once around. Now over here, I've done one rotation, so I'm looking up again, but the sun isn't there anymore because I've moved around. So I need to wait a few minutes, 3 minutes, for the sun and for the Earth to turn a little bit around, and then the sun is again above my head. Done. That's what we define as 24 hours. Therefore, a whole rotation of the Earth is a bit shorter than that, 3 minutes short. Okay. But that's not always the case. That varies, because that's always the case if the sun, if the Earth would be moving around the sun in a circle, i.e. our speed would be this constant speed as we move around. We're moving around in an ellipse. That means we're a bit quicker when we're closer to the sun and a bit slower when we're further away from the sun. Now, quick check. Which time of the season, which time of the year do you think we are closest to the sun? Yes, exactly. Not summer. No, but roughly beginning of January. Yes, beginning of January, we're closest on our arc. That means that's when we are quickest. So actually, that means we're going to be mostly moved along and the Earth has to turn more. So that's where our movement of the 3 minutes doesn't really fully work. So we are overshooting in a sense. If you're going towards the side where we're furthest away in the beginning of July, when you're sitting there at that point, you're slower and your overall average turning as you expect is going to undershoot. So you're over and underestimating the position where it should be. And that's what you're seeing. So we're either under or overshooting as we're going one side to the other side, which happens as we move through the seasons. So that gives you that kind of motion. Okay, that explains a motion left-right. That should give us an oval. Agreed? It's not an oval. It's a weird figure of 8. That's because I've taken into account our elliptical motion. What I haven't taken into account that our Earth's axis is tilted. So the apparent orbit of the sun, i.e. our Earth's orbit, is tilted with respect to our rotational axis. That means the sun is moving seemingly through the stars over a day. Okay, that's fine. So much so that it changes position with respect to the stars, but therefore also is sometimes a little bit higher in the further in the south and sometimes further in the north. So it changes that. So we all agreed the sun will have more or less the same speed as it seemingly moves through the stars, but the direction of the movement will vary. So either if it's, let's say, midsummer, it's highest in its northern position, so it'll move only in one direction, not north or south. But if it's now going down, at that point, we're getting a component that moves north or south. That means how fast it moves east or west in that way direction in which it travels is slightly altered. You'll get it either moving a little bit up front or slower, up front or slower. And if you can think about that happening, it's fastest at midwinter and midsummer, and then slower down in between. That's fastest twice a year, slowest twice a year. That's where you get the double hump. That's where you get the double oscillation combined with a single oscillation, slightly offset, gives you this kind of double oscillation and causes that figure of 8 to happen. And this you can put together to a what's called equation of time, where if you know the date, you can look by how much the sun, the real sun, will be off from the average sun. Because the average sun is what we're sort of assuming would be just up or down. That's what's called the equation of time. And I think it sounds bombastic because it is. Because the equation of time is independent on where you are on Earth, what you're doing or anything. It depends upon the ellipticity of your orbit. It depends on the tilt of your axis. Nothing you can really change by where you are. So it is very much embedded in the planet you're on. So if you're going to Mars, that will have a different one. If you're going to different planets, they will have different equations of time. But you need to know that. So yeah, not a trivial one at all. So that's this kind of figure of 8, this kind of an lemma. So if we move on from that, a meridian sundial, a way in which we want to set a time signal to be able to set our clocks, is a bit like a sundial, but we're simplifying. We're really narrowing down the sundial to the minimum that we require. And we were looking at where the sun is at midday. So let's try to only simplify that by only having what's called the meridian, the north-south line, nothing else. All I want to see is when does the sun cross that line. If I know it crosses that exact north-south line, I know for my location at this current date, it is local midday. All I need to now faff around is how much is the real sun actually different to the average sun. So I've got my average local time. And then, oh, I'm here at this longitude, correct for Greenwich, and I can then shift and therefore calculate exactly for the 21st of January in Nottingham, I would be that many minutes off from Greenwich. See what my clock says, check that, adjust, and you're on time. So that's the idea. And that's what's essentially been created here in Bromley House Library as well. So all they have created is a meridian line on the floor, which is exactly north-south, and an appropriate, well, you can't see that there's actually a big column casting a shadow. They've inverted that. What they created is a little sun disk, a little hole in there that allows the sun to shine through and cast a little disk, a white, a little solar disk on the floor. That's essentially the marker for when you're reading off your meridian sundial. So all you require is that has to be exactly above there, and over it moves. And as soon as it crosses the line, you know that's your midday. Check that, the table's set, and you can go to your big stand-fast clock that they've got in the next room, set, and off you go. And you'll actually see when you're going in there, somebody's nicely noted down exactly how many minutes off it is for today and put that in the back of the clock as they were winding and resetting it over the years as it was working, to make sure that's kept in line. Something that we think, why would you need to do that every day? But these clocks weren't the best. They were ish keeping time, but they needed to be reset. We'll get to that, but actually timepieces that are so good that they would keep the time for prolonged periods were very expensive. If you're talking about the times of the 1880s, 1840s, at that point, you could probably calculate how much a timepiece would cost by the average wage of a captain of a seafaring ship would earn per year. So a substantial amount. So definitely not something that's easy to come by. So sundials or meridian sundials are few still surviving. So in the UK and England, we've got 3/4. So the Custom House in Ramsgate is actually not present anymore at all. You don't find the meridian line. The window itself is only there. What has been the initial little hole is gone as well, leaving us with 3. Durham Cathedral is a beautiful example. Bramshill House, is a very interesting one. What's happening with this, we'll have to see. And our Bromley House Library, sort of on different locations across the UK. So I'll go through some of them. So here, what we'll do is we'll what's called assess the functionality and how well they're preserved. So functionality means that we will look at the meridian line. How well is that oriented? Is that really north-south? The next part, looking at, does that actual aperture that sits here, is that exactly located above the line? That's what you want. You want the perfect line that's north-south, and the hole needs to be exactly above that. If it's off, that will give you a misreading. It's on there, but the line is tilted. That will give you a misreading as well. So looking at Durham Cathedral, there's the hole. I've always tried to spot that in Harry Potter movies, but I've never managed. But you can see sort of it features in some of the Harry Potter movies. You can see the arches, but one of them is filled in and there's just a hole left. That's the original one that's been set in there. And it has an indication on the floor, but actually it comes up on the reverse wall as a meridian line. You can just about see it in here. I've highlighted it a little bit more in my drawings. You can see the line. It looks quite poor because it is sandstone, and you can see how the seats are set against that, and that just invites graffiti and erosion. So this line would go on here, but the surfaces are so eroded. So it's in a worrying state, I personally find, of conservation in here as well. But there's a line in there. We've surveyed that using a, you can see this one, previous one. I've used a good old optomechanical theodolite. So what I did is set that up exactly above the meridian line, and then took solar azimuth to ensure that I get the right orientation, and then use that to survey the orientation of these lines. Doing so, we then found for this case that they are close to, but still slightly misaligned, for 5 to 14 arc minutes to the east. But the aperture is bang on above the line. That's really good in this case. Bramshill is slightly different. It's also very odd. It's also the oldest of the lot. So I'm standing currently on a kind of first floor balcony, and that used to be a side of the building that they then opened up as an alcove. But having opened that up, it's very strange. That used to be a room, and that used to be a bay window. So what they did is they opened that up, and the chap owning that beforehand had the vision, having come back from Florence and his tour of Italy, that he's seen these installed. He wanted one like that. So he filled in, you can see the bay window. There's the little corner where he's got that. To not spoil the view from the outside, you can still see the windows. They're just bricked up. It doesn't make it a better projection. But there's your dot on the floor. You can see it was a police college. White was the leading color there, and it's been painted over. And really effectively, you can see slowly but surely the paint has started to fill in the hole as well. And you can see here, that's a ground plan from the aperture right to the column which sits over here, and you can see the floor has suffered. So, but in parts, you can still ensure that you can see this meridian line as it's set. So that one, you can see it's substantially misaligned, but you would expect that because it's one of the earliest ones, and the kind of idea that I think there were more after the idea. I just feel like I want some experience like it was in Italy when I saw it in beautiful churches in Florence or so. That's what they wanted to achieve. Now let's have a look at Bromley House, the situation. That's an interesting building. Some of you might have visited Bromley House Library, not sure. It's definitely a jewel in Nottingham for sure. It's just, if you've been on Market Square, got off on the buses from there, it is just along there, Angel Row, so really close. So here you're in the garden. Just on the other side is the busy Market Square. So it's a beautiful, I think it's one of the very few, 2, 3 or so, unaltered Georgian town gardens that you found in Nottingham as well. So it's a beautiful, quiet spot. But it is per se a townhouse built 1752 and then turned into a library. So definitely not ideal if you're thinking about the amount of weight of books and where they can be placed. So there are lots of ramifications. You can see that it was a house that's been turned into a library. But bits coming through here, you can see this is a timeline developed by one of my students, 2017. He's picked out that, for example, George Green, some of you might recall him as a mathematician, was a member of the Bromley House Library as well. And then we come through 1834 was the first mention of the Meridian line. Now, don't think about grand, oh, this is our idea, this is how we're going to plan it, I'm going to ask so-and-so to construct it, we'll draw a plan. No, you have to think about what will be noted in meeting notes of the library. Well, expenditure, what's been paid for. So 1834 is the first mention where they said that they needed to purchase that much brass for the line to put it in place. And that's the first and only mention of the Meridian line. Job done. Nothing further. So we have no idea who built it, necessarily why and how. It's not there. And also, if you see 1834, they set it in brass, i.e. noticed how much they paid for it. That's it. That's in the notes, nothing else. You will know that that's not when they constructed it the first time. If you set something in brass, you will very much make sure that whatever you're doing it and it works. So they probably will have worked on that easily a year, 2 or 3 beforehand to ensure that works. But now let's add a few other bits. So you can see 1839, and I've highlighted that here, 1840. That's where you then start putting in the railway into Nottingham. So actually, this happened considerably before all the malarkey of unified time and trains arriving here. So you can see the narrative we wanted to spin initially. Oh, this was installed to ensure that we can keep the time, and so might not be perfectly true. So actually what's probably more realistic is that it's what's called a Wunderkammer. So it's a library for the Gentile of the time. And because they were educated and had books, they wanted to showcase that we are educated people, we know sciences, we know nature, therefore we will have a barometer, which I have. We will have a wind vane hooked up that will note how much wind and in which direction it was blowing. And therefore they will also need a timepiece. So they've got a clock in there that keeps time. And if you see that steadfast clock in there, you'll see the engravings where it says how many minutes is different to St. Paul's, for example, as well. But they will also require Meridian Sundial to be put in place. Not because they need it for timekeeping of the clocks initially, but because it is a piece of what the gentlemen of the time that are well educated would have in their collection. Still doesn't rule out that it's a perfect use, and people will have come set their clocks, taken it back to their estates, and then use that to set their clocks as well. And then it disappeared, was covered by linoleum and carpets, and then 1998, Douglas Bateman then uncovered that, and there's the first remnants of the beautiful brass line as it comes. And at the moment, it's now nicely set in the carpet with brass line and covered, so you can see that as well. So we measured the same things here as well. This is a view from through my theodolite, and you can see I'm situated exactly on the Meridian line on the far end, viewing exactly along here, and you can see there's the aperture and there's the center of the line. So the aperture is just missing that. So we're not exactly on the Meridian line, we're off center of that. I'm exaggerating. Also, the whole Meridian line is slightly tilted by more or less 5 arc minutes as well. One thing to point out is that where in the other cases you saw the original Meridian line and the original aperture, here what you're seeing is the original Meridian line, but a replica aperture. The window is still there, but the aperture is not. So what has been put in place is an aluminium replica of that at the front of the window. And I'm very sure that most likely it will be something that this is offset, because it should be in this position as it's done, but on the other side or set further back. So the position is correct as I would have measured it from the old panel they still had, which doesn't fit that window, but just offset. But we're exploring that currently. And that's what my current project student is doing, Matt, who will be hopefully talking about this a little bit more in depth on the Thursday. So I'll just give you a little hint. So what he's done is with me together, there you can see our handheld 3D scanner. We scanned the entire site in more detail rather than just measuring it up to create a 3D working model in Stellarium itself. So we can model how that would look like. And if it's in the Stellarium, then you can easily just take that panel and move it further back to where you think it would work. So we could explore that in a little bit more depth. And this is the bit where I'll exit mine and go into Stellarium, which I was showing you just beforehand in here. There we are. But what I will do is I'll now bring up, now ignore the landscape, but I'll bring up the room. Here it is. And you can see there's the window. There's a seat where you can sit. You can see the aperture sitting in there. But what you can also see, just make sure we've got a sensible time. That actually doesn't show us the moon shining through as a shadow. But there we are. There you can see, apart from all the other horrible bits, because there's just a simulation that shows you the key things. Oh, I like that you can see the trees, which you won't. You can see the nice shadow being cast down there. And you can see how that changes as we go through time. You can see that as I move in time, there's your beautiful brass line. There's a few artifacts of the simulation. And as that moves in, there we are. There's now running onto the line, and you can simulate how it moves through. What this is by far is a simplistic shadow casting. It doesn't bring in all the horrible half shadow problems that you'll get as well. But it's an ideal one where we could now see how the situation is, compare with the survey work, but then also take this panel and move it to the other side of the window to actually see what happens. So that's some of the work that we're doing. Just get rid of that and default back to the presentation. So that's what we're currently doing. And what I'll now hark to is what a past student has done with me in another work talking about this, which goes more into the construction method of this. So we've seen how the simulation might work and tell us a little bit more about it. But what else can we learn from this? For one, how would we build a kind of Meridian sundial? Well, okay, easy to have a hole. The next bit, we need to draw a line or create a straight line. Straight line is okay, but how would I ensure it's north-south? Not only ish, but it needs to be precise. So if you're thinking about this, you would use a compass, or happy with that? Yes? No? Why? Who's saying no? So why would a compass not be good? It's not true north. I love it, because actually is it more or less now for our location in the UK, it's more or less not bad on true north, because it's just about that point where we don't have any change in that, because the magnetic north and geographic north are for us in the UK for most parts in the same direction. But it's worse than that. Have you ever tried to use your compass indoor? I can do that in my office, and I can tell you north is either there or there, depending if I'm close to the heating, to my computer, to other lines and the wall or so. Now, that's just mine. Now, if you go into a Georgian townhouse with good old ironworks going through, forget about anything of that. And also, if you're working with compass anyway, you would remove any iron and stay away from houses to use it precise. If you've done any orienteering, you will know that. So, yeah, there's a big problem with that part. What else could we do? Well, another one before I go into this is using clocks. So if I know how late it is, I can use shadows, can't I? So I can go wait till it's exactly midday, see how the shadow falls. If I'm clever enough knowing the times and everything like that to tweak, I can get the sun to be exactly due south. Brilliant. You can see there's a chicken and egg problem here, because for that, I need a perfect clock that has been synced and works exactly. Now, we could do that for Bromley House, 1840, but we would have to have gotten an appropriate timepiece. We're not talking about clock at that, we're talking timepiece. Ones that they would take when, for example, Shackleton would have taken 3 or 4 on his adventures. These kind of timepieces we're talking about. So serious money. So don't ignore a computer, that's peanuts. You would be talking about, take something along that's equally as much worth as the house you're living in. So that's the kind of clock you would talk about. Possible, but maybe there's other ways in which you could have done it. Well, if you're thinking about that, you could use stars. to create a north-south line. You could look at where Polaris is, the North Star. And if you could line that up, you have an idea where north is, and you could start building and setting things up. So that's, again, one option where you could do that. But where the clock is a possibility, but it's far too expensive. Compasses, forget about them because you got all the misreading. Polaris, if you remember my little image of the library, it had a south-facing window. Yeah. So if you're in that building looking out of the south-facing window, forget about seeing Polaris. Okay, maybe there's some weird thing where they backtrack, where they went into the garden so they could look over the house and see Polaris and then shoot a line across in there and construct something. But you can't go far enough back in the garden. The house is still too close. You'll never see low enough to actually see Polaris. Gives you another problem. So there's not really a way in doing it. But there might be another one. Shadows, isn't it? So if you look at shadows, okay, we can use the sun as an indication. And a good one is, yeah, so if the sun is due north, due south, highest in the sky, your shadows are shortest. Good. So why not do that? Look when the shadows are shortest. When they're shortest, you know it's bang on south. So therefore, you've got a nice line that you can draw. We'll get to that. Bit problematic. The other one is what's called the Indian circle method, which is a little bit more complex, but actually harks back to times where we didn't even have writing. It predates and goes into the prehistoric, you think. So at that point, what we need is we need a shadow caster. In goes the shadow caster. Then we need string, and that's where it ends. I don't need anything for it. In goes the shadow caster. It will cast a shadow on the ground. What I'll do is then use string to draw a circle around the base of my stick that has cast a shadow. And now all I need to do is have patience. I need to see as the sun rises and sets, my shadow will move across. And at that point, I can now mark off where the shadow moves. Oh, it's crossing my circle here. Mark that point. It crosses the circle again. Mark that point. And what I've got now is 2 points that are nicely east-west. All I need to do is create a line that's perpendicular to that. Again, see how good your geometry is. I need to draw 2 circles of equal radius around these 2 points. They'll intersect, connect these two, and out come a perfect line that's perpendicular to the east-west, i.e. perfectly north-south. Jobs are done. Why you might that? I don't understand how does that work. You do in a sense, because if you were able to see a perfect horizon, you could see how the sun rises and how the sun sets. If I see these 2 points, I'll just take the middle, don't I? I don't have access to that because the horizon is horribly with houses and trees and whatever. But what I've created with this circle is an artificial horizon. I'm picking out 2 points where the shadow is of an equal length, i.e. the sun is at the same height. So all I'm doing is I'm waiting till the sun reaches that height and that height again. These are 2 shadows here and here. Basic geometry that we're using. So simple in its construction that it's easily predating pyramids, for sure. So 2 things, shorter shadow or an in-circle method. And that's what my student has done. I won't elaborate too much on this. If you want to, I can do so. We did what's called a Monte Carlo simulation. So we, in the computer, simulated how that would happen. And doing so, you would assume these points, the circle might not be perfectly drawn, the points might not be perfectly, there's a certain randomness coming in. Giving the randomness, you can then see how much your line would be created. So it might be a bit like that, this time a bit like this time sort of a bit of variation. So, and that you could create the kind of typical kind of variation that you'll be getting. And doing that, you have to expect how much does that string stretch while you're working and so on. And as you're doing so, what you can do is now do that and read off as well where the shadow actually, where the sun disk actually falls. Because in the picture here before, you can see this is a simulated shadow, and I've got pictures, loads of that, where you can see these discs of the sun falling on the floor. But what you can see is very different to my simulation on Stellarium. That's not a sharp circle. It's a very fuzzy circle. So at that point, it's also not a nice crosshair, which we would love to say where the center is. Actually, I need to look at this fuzzy blob and be able to say, well, if that's a fuzzy blob, I think the middle is there. And that's how you have to determine where it is. And that's what factors into this kind of Monte Carlo simulation as well. That kind of uncertainty. Knowing that kind of uncertainty, you look at the blob and say, oh, that's where it is, that's where it is, that's where it is. You can sort of now measure how far away is the shadow from that little sun disk from the aperture. And that's what you're plotting here. And it's that far away, it gets closer and then moves further away over midday. Okay. So if that's happening over midday, that doesn't look really nice and smooth. It wouldn't, because there's a fairly randomness. It's not a really nice crosshair as you're determining where that is. So that scatters substantially. And that's what we've had with participants that looked at the sun disk and tried to determine where the center is. So actually, at best, you could say that's the kind of error range of determining where the sun would be distant-wise. But that means actually there's a good span. The sun gets to a certain point where the shadows are shortish, and at that point, that's within the errors. It jumps, you're not sure, is it now, was it then, is it going to be later? So there's a range of times where within errors, you can say anywhere from here to here, you're hitting the shortest shadows. As you're looking at your data, that's what you can see. That somewhere in that range is where your shortest shadow really is. That means actually, that's 13 minutes uncertainty, give or take 6-7 minutes. So at that point, yeah, that's substantial. If you're looking at 13 minutes, that means the sun has 13 minutes time to travel east to west, due south. So it's either there, or there. Actually, you're getting it at the time where it's worst, because the sun moves quickest across the sky from east to west. So as that happens, you can then translate that time into uncertainty of a good 3 degrees. It's good, but we can do better. So using that very simple method, you can get a south direction, but only ish, because you're still substantially off using that method. But I'm not going into the diagrams too much. What actually you do, if you're doing it with the Indian circle method, you can get much more precise values. Values that range depending on how wisely you choose your baseline, how far apart the points are, up to 20 to around about 20 arc minutes precision, which is more or less where we can show that this is far more superior to the shorter shadow method. So that's most likely, if you wanted to use shadows, how you would do this. But also that gives you an idea that there's a precision that sits in here, which is quite close to the kind of misreadings that we found when we were measuring. We got these kind of misreadings. They weren't less than an arc minute, nor were they more than a degree, apart from the very first one. So they were in the range of what we would expect here as well. Good. That's what he sort of summarized, my student, while talking about this. But what is interesting, which I'll put in here in the next one, is that while you're doing this, there's a following that you have to envisage. So as the sun rises and sets, the shadow moves across here. Now, if you look at the room as it's been set up, you can see the room is not north-south. It's been a random house that they've been selected. So there's your window. There's the meridian line going at an angle. So that means actually at one point when you're going towards AM versus PM, you'll see a substantial amount of variation in the shape of that line. So it will be very more distorted on one side compared to the other side. That means your reading of where that sun disk would be exactly on the ground will be more problematic on one side than on the other side. And that's what we've done here. Loads of measurements of participants that looked at these disks that said there's a center, and we've compared that with the model. And what we found is that on the one side, they scatter more or less around the typical value where they are. That's the quite undistorted ones. These are the quite distorted ones where we have a big problem as a human identifying where the center is. That means that actually we get a value that's quite close to this, which is significantly different to, or just about at the edge of significantly different to what the predicted value should be. So that's interesting because this is a very subtle hint of a systematic error that comes in how you were doing this. If this were all nice symmetric, you wouldn't see that, because the line is at an angle and the aperture is at an angle, and the distortion is different on one side than the other, your reading of where the disc is, and therefore your geometry is slightly distorted. That amount tilted ever so slightly. And actually it tilted by, in my calculations, by roughly 4 arc minutes. Remember by how much the line was tilted? 4 arc minutes in the same direction. Now, that's not proof, but it's a strong argument that there might be a hint in the misalignment indicating the construction method that has happened here. So, moving on from here, I think what this can show, and hopefully has shown, that these Meridian sundials, with their quirkiness of how simplistic they're reducing sundials and using them as kind of time signals, are really, really exciting examples of some kind of the science of time and measuring time and defining across. But it's also shown that they are around, but they're definitely not protected. And they're definitely in need of looking after in more depth. What we've also shown specifically for the Bromley House case is, rather than showing that the Indian circle is used, but it's definitely one method that allows you to quite precisely set this up, and it makes a strong case of it have been used for the orientation of that line. What we propose is, given the kind of setup and approaching it from this is how they might have been set up, is that actually on the line itself, when they were renovating, they didn't see any markings. But actually, when we're looking at how it would be constructed, hardly any markings would be on the line anyway. They would be all off-center. Actually, ideally, as far away as possible, our construction methods actually predict there are certain patches on the ground where there most likely would have been marks on the ground to mark off where the shadow would have traveled. So if we wanted to confirm that, if they wanted to take up the carpet, there's certain areas they could look into onto the wooden floor. If there's markings, carvings, or anything left behind that could indicate a possible hint of how this was constructed. But this all comes about that there is no written evidence who did this or how they did this. But hopefully you've seen some ideas how that might have been done and how that relates to some beautiful basic celestial mechanics. Okay, at that point, I'll rest my case. Thank you very much, everyone.